So we're going to start with the anatomy of the lungs, and that's going to be on not about figures 17.2, 17.4. And the first thing we're going to talk about is that the lungs, the main tube is called a trachea. What I'm drawing here is I'm drawing the tracheal tube, which, if you recall, is lined with a type of epithelial tissue called pseudostratified columnar epithelium, and it's called that because it's mainly goblet cells that secrete mucus. We'll talk about mucus a lot in chapter 17. But anyways, the trachea is held patent with incomplete rings of cartilage. These are C-shaped rings like this. And the reason why they are C-shaped is because just posterior to the trachea, there's going to be another tube called the esophagus. And you don't want the esophagus to be rubbing too much against those the cartilaginous bone, because if that was to happen, then it would cause friction and then damage over time. Okay, so the trachea is held open over via these incomplete rings of cartilage. So the trachea is going to be the main, I guess they call, windpipe. Now I'm going to draw here one tube that is going to go rather, that is going to go almost straight down, then another tube here that's going to go more to the side. And these are called the left and the right primary bronchi. Let me see if I can do this one a little bigger. So the trachea is going to segregate here into the left and right primary bronchi. And these also are going to have rings of cartilage to keep them patent. So we have here the left and the right primary bronchi. So these here, I should have done them in a different color, shouldn't I? But these here are the primary bronchi. And they are going to further separate into secondary bronchi. And we are going to get more and more divisions. So we're going to see is that these primary bronchi are going to begin to branch off here like this. We're going to see that these are also going to have some incomplete rings of cartilage. But then the further bronchi divisions, they are going to be known as eventually they are going to be known as the bronchioles. And they are going to have mainly made up of smooth muscle. So I'm not going to draw a lot of these, but I'll draw a couple just to give us an idea here. See that they're going to keep on doing these fractal divisions. And that's the one interesting thing about the bronchial tree, which I believe, if my knowledge of Latin is still holding up, that bronchiole means tree. And if you think about the bronchial structure, if you turn it the right side up, it kind of looks like a tree. So we have the trachea, the primary bronchi, and they're going to branch off to secondary divisions, and then you are going to have the bronchioles eventually, and the bronchioles are going to terminate at sacs called the alveoli. I'll draw a couple of alveoli sacs. This is not really true to life, as we say, but it kind of gives you an idea. And these actually are the functional units of the lungs, which we'll talk about. So now we're going to draw the actual lung sac. It's going to look something like this. Going to go down like this. You're going to see division up here. And that's because the bottom is going to be a muscle called the diaphragm. So I know these are not the prettiest lungs in the world, but it will give you an idea exactly how they look. Okay, so these are going to be the bags of the lungs, as they say. And of course, there's going to be many more divisions of what we see here. So we have up here the trachea, which is held patent by these incomplete rings of cartilage. Then we have the primary bronchi. We're going to have further divisions until we get to the bronchioles, which are tubes that are mainly comprised of smooth muscle. And then at the end, we're going to have alveoli, which I drew here in pink. And the alveoli are the functional units of the lungs. And let's go ahead and talk about those alveoli. So alveoli, these are the functional units of the lungs because they are a site of gas exchange. So these are functional units, as they are the site of gas exchange. And they are composed of two types of cells. Type 1 alveolar cells and type 2 alveolar cells. And I'll kind of draw you some examples here. So these ones in pink, I'm going to say are type 1 alveolar cells. And here in orange, and these only make up about 20% of the cells, but here in orange is called a type 2 alveolar cell. So type 2 alveolar cell. And then the ones in pinks are going to be type 1 alveolar cells. And the type 1 alveolar cells have a unique distinction, is that they're going to secrete a compound called surfactant. Surfactant is going to oppose a property of water called surface tension. So type 2 alveolar cells, they secrete surfactant. And the job of surfactant is to decrease surface tension, a property of water that we'll talk about later. If there's an absence of surfactant secretion, it normally is seen in babies who are born premature, and it's I think it's called infant respiratory syndrome, and it's caused by a lack of surfactant, which makes it difficult for the alveoli to expand. Very important that the alveoli expand with gases because they need to diffuse into the blood. Now, so yes, this is the alveoli. And what's interesting enough is that the SARS-2 virus actually infects these alveolar type 2 cells, which we'll talk about in a bit. All right, so I guess I was a bit premature in obliterating my lung model, but it's okay. I can draw one again pretty quickly. Yeah, this isn't perfect, but you'll get the idea. So we have our lungs, a very healthy set of lungs on this individual. Now the question is how are we currently breathing? Are we vacuuming air in our lungs like a one of those high-end Dyson models, or is there another way? And the answer is that breathing is actually a passive process. However, expanding your lungs is an active process. Because on the bottom of your lungs is going to be a muscle called the diaphragm. And what that does is it is going to take your lungs and it's going to expand them lengthwise. So to give you an example, the diaphragm, if these are your lungs, when it contracts, it's going to look like this. So it's going to stretch them like this. It's going to, because your lungs are actually very elastic. So it's going to stretch them up. And by doing that, it's going to increase the volume. There's also muscles that are attached to your ribs, and they are called intercostals. Now, what the intercostals do is they're going to take your muscles, sorry, your lungs, and they're going to lengthen them like an accordion. So more or less what you are doing, if you want a visualization of what's going on, of course you do, you're watching this video, is it's going to take your lungs like this, and it's going to do this. It's going to greatly increase the size. And you can feel this if you just put your hands right about where the diaphragm is and just inhale deeply. You can feel it contract. When the diaphragm contracts, it's going to flatten. When the intercostals expand, well, they're going to expand. And of course, these are skeletal muscles. So expanding your lungs is an active process. Breathing, though, is passive. And we're going to talk about that here. So that kind of gives us a very interesting question. How do we expand the lungs? The lungs are just an elastic bag. They actually don't do anything, really. It's the muscles that must be responsible for that. The muscles must be responsible for expanding the size of the lungs. But that comes another question: how? Are the muscles permanently attached to your lungs? And the answer is no. So let's go back here and let's talk about cavities. The lungs are encased in what is called a pleural. All right, so now we're going to be talking about another essential part of the lung anatomy, and that is going to be the pleural membranes. The pleural membranes are actually consist of two membranes. One is going to be called the visceral pleural membrane, and the visceral membrane is unique because it's basically continuous with the actual lungs. Recall that the lungs are extremely stretchy, and the visceral layer is going to be more or less the outer aspect of the lungs, if you want to consider it that. But if you were to take out somebody's lungs, then you'll see that the very top layer is going to be the pleural membrane. So the visceral membrane is basically continuous with the lungs on the outside. Now, the lungs sit in a cavity, the thoracic cavity. And the thoracic cavity is closed from the outside environment, as I'm sure you know. And I'm just going to draw here in black. I'm going to draw the walls of the thoracics, like so. So right now we have a space here between the lungs and the thoracics. That here can't really be the case. We can't have a space because we need something to expand the lungs. You recall me saying is that respiration is an active process. It's active because the muscles expand the lungs, which causes gases to move in and out of the lungs. So if you remember here, we have the diaphragm and the intercostals. So we need something that's going to stick the lungs to the walls of the thoracic. And to do so, we have another membrane, and this one is going to be called the parietal membrane. And the parietal membrane is more or less continuous with the thoracic cavity. So it is going to run like this, I'll say. Isn't a perfect diagram, but you get the idea here. Okay, so it's going to run like this. And if you look closely, you'll see that the visceral membrane and the parietal membrane are not actually touching. In fact, there's a space there. I'll call this the pleural space. That's not a real term, I don't think. And the pleural space is a potential space. It really isn't a space. It is a potential space. And to zoom in a bit, it's going to look like this. So this is going to be the visceral membrane. This is going to be the parietal membrane. And this here is going to be the space. Now, that space is not empty air, of course. That space is actually going to be liquid, which we'll just go ahead and call pleural liquid. Again, I don't think that's a real term. I think it's just fluid. There's not much in here, maybe about 25 milliliters. But what this does, and I'll kind of shade this in sky blue so you kind of see here. So what this does is it is going to allow the visceral membrane to stick with the parietal membrane. How it does that is through a property of water called cohesion and adhesion. It's a property of water that states that water wants to form bonds with other water molecules, and if it can't form bonds with other water molecules, it will form bonds with solid objects. That's why you can pour water on your table. Eventually, it's going to go like this. So you have a table, you spill some water. I'm sure those of you with kids know that they're very good at that. I know my niece is an expert. Water is going to spill like so. Then eventually it's going to collect onto a puddle like this. It's because this border here, water molecules have formed bonds with the solid objects around it. It almost like anchors itself. It's a property of water. Now, because of the properties of cohesion and adhesion, and the fact that this is basically more or less an airtight space, it allows the liquid allows the two aspects of the pleural membrane to form what's called negative pressure. And yes, in case any of you want to jump in and correct me on this video, I know negative pressure is not really a thing. The correct term is vacuum, but old habits are hard to break. So what this negative pressure is doing is it's basically keeping the two pleural membranes sticking to each other. So what this does is that and I know I didn't draw this to do justice, but the parietal membrane is basically continuous with the walls of the thoracics, which includes the diaphragm and the intercostals. When the diaphragm contracts and the intercostals expand, it's going to pull along the parietal membrane with it. However, the lungs and the visceral membrane, without being stuck to that parietal membrane, they really are not able to inflate. So one thing to keep in mind is that the lungs are always partially inflated. This will come in handy later to know. But the lungs are always partially inflated. And that is because the thoracic cage is never completely collapsed. It's always somewhat open. So what happened is that the parietal membrane is continuous with the thoracic walls, and if the system is functioning normally, the visceral membrane is going to be stuck to the parietal membrane. Because of that, if you exhale normally, your lungs are going to be partially expanded. Now let's say that you try to exhale out as forcefully as you can. Your lungs will still be partially inflated because they're attached to the walls of the thoracic. However, that can change if something happens called a pneumothorax. And that is a very serious condition. Let me make sure I spell this right. One of those words that I'm so used to writing wrong that I don't know how to do it right. Yeah, there we go. And this is a loss of negative pressure in pleural space. What's going to happen here is that there's going to be some kind of puncture wound that is going to open is going to create a tunnel, I guess you can call it, that connects the atmosphere with the inside of the thoracic. What it's going to do is if it is sharp enough to penetrate the parietal pleural membrane, what's going to happen is you are going to have a loss here of negative pressure. And why is that? Because that cut has caused the thoracic cavity and the atmosphere to reach equilibrium. And note that the atmospheric pressure is positive. So what's going to happen is that the pressure between the two pleural membranes is going to be positive. The result is going to be this. So this is a set of lungs where here I'll draw a comparison actually. So this is going to be a set of lungs normally. So this is just everyday normal lungs. Okay, and I'll draw another one here. Well, actually, let me finish drawing this one. So we'll say that pink is going to be the visceral membrane. And we're going to say light green is going to be the parietal membrane. And recall the parietal membrane sticks to the walls of the thoracics. So this is normal. Now let's look at quote unquote collapsed. What's going to look like is this. I'll just say that one lung is going to be collapsed. Because recall that there's two separate cavities basically. What's going to happen here is that you see that the visceral membrane is still attached. However, we no longer have the two pleural membranes connected. Whereas on the other lung, we see that it is still intact. So what we've seen here is that there's been some sort of incision that has penetrated the thoracic cavity. What's happened here is that you've had a loss of negative pressure. This loss of negative pressure has created a positive pressure environment, and the two pleural membranes are no longer sticking together. That's what happens during a pneumothorax. And yes, it can be fixed. Probably the EMTs in the class can tell you a lot better than I can, but I do believe it involves vacuuming out air from the thoracic cavity. But as I said, they can definitely explain it better than me. All right, moving on to the next one. All right, so now we're on to gas exchange. And let's go ahead and let's talk about exactly what the functional units of the lungs do. These functional units, if you remember, they're called alveoli. If you remember too, we have two kinds of alveolar cells. We have alveolar type 1, alveolar type 2. We're just going to draw the alveoli here. Now we also know that there is a fluid medium in the blood, well, called blood. So we have our blood. Then we have here a space. So let me go ahead and label these here. So we have the alveoli, functional unit of the lungs. We have the blood. Then we have this space here called the interstitial space. What's going to happen here is that gases are going to enter the alveoli. The two main gases that enter the alveoli are O2 and CO2. Now, what's going to happen is that CO2 is also present in the blood in rather large amounts, and oxygen is also present in the blood. But by the time it gets to the alveoli, it's rather depleted of oxygen. So what's going to happen here is that at the site of the alveoli, we'll say that this is going to be the venous end. At the site of the alveoli, you're going to have two concentration gradients. Carbon dioxide is going to be in a higher concentration in the blood. Actually, I did that the wrong color. Let me change it or else it'll bother me. Okay. So we see that CO2 is actually higher in the blood than it is in the alveoli. Now we see that the inverse is true with oxygen. Oxygen is in larger concentrations in the alveoli, and it's in smaller concentrations in the blood. So we have a concentration gradient. Gases also go down their own concentration gradient. What's going to happen here is that oxygen is going to diffuse into the blood, and CO2 is going to diffuse out of the blood and into the alveoli. Now, these two environments that I wrote down are just between the blood and the alveoli. The atmosphere is another story. Because in the atmosphere, there's very little CO2. I know we talk about climate change and things like that, but comparatively, there's very little CO2. So I don't want to mess up this diagram too much, but there's less CO2 in the atmosphere than there is the alveoli, and there's more oxygen in the atmosphere than the alveoli. So CO2 is going to always diffuse out of the alveoli or lungs, and oxygen is always going to go in, assuming that conditions are normal, assuming that we're at atmospheric conditions. So more or less, carbon dioxide is going to diffuse from the blood to the alveoli, and oxygen is going to diffuse from the alveoli to the blood. And that's how gas exchange occurs there. All right, so now we're going to talk about mucus secretion. And as we know about mucus, well, it is a very sticky compound. And the idea behind mucus is that it's supposed to capture foreign objects as they go into the respiratory passageways. Does a very good job of it. What it does is it's constantly being wafted up by the cilia, and you can see the cilia on a stained microscope slide of the pseudostratified columnar epithelium. But these cells, they actually have something else built in them, is they're goblet cells. So they are going to secrete mucus. The problem is that mucus is going to be way too thick unless we can water it down a bit with saline. So we're going to talk about how that exactly is made. So I'm going to draw here two adjacent cells. And this cell here, we're going to build in a goodie. It's going to be the NKCC symporter. And we'll be talking about this one a bit. So this is going to be our main symporter. It is called the NKCC because it is going to transport Na plus, K plus, 2Cl minus, NKCC symporter, because it's all going in the same direction. Now we also have our good friend, the sodium-potassium pump. And then we're going to have a channel here that we don't, and I don't talk about the leak channels, but for this example here, I do need to acknowledge it, or else I'd be only telling half the story. We'll be having a K plus leak channel. Okay, and also there's one more thing I got to build in, very important. This is going to be the CFTR channel. Okay, so what's going to happen is that the NKCC symporter is going to move in exactly as advertised. It's going to move in potassium, 2 sodiums, sorry, 1 sodium, and two chlorines. So by doing this, you balance out the charges. But we have to do something about the ion distribution. All right, easy enough. What's going to happen is that first the ions are going to be transported in. Potassium is going to leave via the potassium leak channel. That's going to go back outside the cell. Sodium is going to leave via the Na plus K plus pump. So we're going to see the ion movement look like this. So we have the actions of the NKCC symporter, brings in 1 sodium, 1 potassium, and 2 chlorines, balances out the charges. And then what's going to happen is that the potassium is going to eventually leave via a leak channel. Sodium is going to leave via the sodium-potassium pump. And then there will be potassium added via the sodium-potassium pump as well. What's going to happen is that sodium is also going to move through a paracellular transport pathway. It's actually going to be pulled along, and I believe it's due to the movement of the chlorine. It's going to establish an electrochemical gradient that's going to pull along sodium in the pericellular pathway. There's a saying that you'll probably be hearing in nursing school a lot: water follows sodium. So you're going to see water moving also down this pericellular pathway. And then you are going to have chlorine move through this channel here called the CFTR channel. It's a functional chlorine transporter. What's going to happen is on the apical side of the membrane, what's going to happen is that you're going to have the presence of sodium, you're going to have the presence of chlorine, and then you're going to have the presence of water, which is going to create a nice saline liquid in addition to the mucus. Now, what about cystic fibrosis? What's that? Well, cystic fibrosis is a condition where, let me get some space here. Cystic fibrosis is a condition where the mucus is very hard, sticky, and very, very difficult to move. So because of that, instead of the mucus being diluted with saline and being able to move up the mucociliary escalator, which wafts up the mucus to the mouth, instead what's going to happen is you're going to have very thick, immovable mucus. Let me go ahead and write that here. So we have cystic fibrosis, and it's going to be caused by a dysfunctional CFTR channel. So what's actually going to happen is that there's going to be an inherited mutation. It is a recessive disorder where the CFTR channel is going to be mutated and it's not going to work properly. What's going to happen here is that you are not going to have the movement of the chlorine into the apical membrane. And if you don't have movement of the chlorine into the apical membrane, then sodium is not going to be dragged along. If sodium isn't dragged along, then you're not going to have the osmotic gradient that's going to pull along water. So it is caused by a dysfunctional CFTR channel, going to be characterized by no ion movement through apical membrane and thick mucus. I know that people that have cystic fibrosis are prone to many more respiratory infections. I believe there are therapies here, therapies for it now that can significantly extend quality of life. But I know that it is a condition that results in a lot of complications as well. Okay, everyone, now for the real reason why you signed up for this course, gas laws. Now, we talked about how the lungs are really just bags. They're bags filled with functional units called alveoli, but in order for those bags to be effective, they need to be able to inflate with air, specifically oxygen-rich air. And gas laws explain exactly why our lungs work as effectively as they do. There's a couple laws that we need to talk about. One is called the ideal gas equation. Ideal gas law. Then we have Boyle's law. And then we have Dalton's law of partial pressure. I'll just put down, Dalton's law. So first, let's talk about the ideal gas equation. You may remember this one from chemistry. And it looks like this. PV equals nRT. So in case you're curious what each of these means, P is pressure, V is volume, N is number of moles, hashtag moles, R is your constant value, and T is going to be temperature. But we're dealing with the human body here. Because of that, we assume that moles is basically constant. Temperature is basically constant. We don't need to include the constant. So if we, so all we're left now is pressure and volume, and you can actually rewrite this equation as V equals 1 over P. So what does this mean? And this is a very important concept with the lungs. Volume and pressure are inversely related. So that's what the ideal gas law tells us about lung function. Now we know that pressure equals forces against the walls of the container. Volume is the space inside a container. Therefore, the smaller the container, the higher the pressure. The larger the container, the smaller the pressure. And we'll talk about that more in our next one called Boyle's law. Boyle's law kind of builds on this a bit. Boyle's law. And Boyle's law states that if temperature and I'll just put down amounts of gas is constant, then pressure and volume will be inversely related. So what this means is that the equation is P1V1 equals P2V2. These values will always be inversely related. Now, what does that mean? Well, I'm going to draw here two squares. And you're going to see the only way that these squares differ is going to be by their volume. Now, each square has the exact same amount of gas in it. So I'm going to put here that volume equals 200 liters. Volume equals 100 liters. Pressure in this one, though, is going to equal, I'll just say, 300 millimeters of mercury. And we see here that in this one, we're going to say that pressure equals 150 millimeters of mercury. So what this is telling us is that if the amount of gas is kept the same, and that's a very important thing, you're keeping the gas trapped inside the same. If you decrease the volume, you increase the pressure, and If you increase the volume, you decrease the pressure. Now this mimics how the lungs work, because with the lungs, we are constantly stretching them open. We're constantly increasing their size through contracting the diaphragm and expanding the intercostals. We're constantly making the container bigger and smaller, bigger, smaller, so on and so forth. And because of that, we can change the pressure inside of the lungs. Now that goes to our third one, which is going to be Dalton's law of partial pressure. Dalton's law of partial pressure. And to summarize this one, sum of each individual gas comprises total systematic pressure. However, and I'm kind of adding this one in myself, each gas travels down its own gradient, called a partial pressure gradient. Okay, so Dalton's law of partial pressure, sum of each individual gas comprises total systematic pressure, and each gas travels down its own gradient. So our baseline is going to be atmospheric pressure. I'll abbreviate it ATM, atmospheric pressure. At sea level, the pressure is about 760 millimeters of mercury. However, the vast majority of that is going to be nitrogen. We don't even count nitrogen. It's very stable, and it's very non-reactive. But about, I would say, 20% of the atmospheric pressure is going to be oxygen. So let me multiply that. So it's going to be about, I'll just say, oxygen is going to be about 160 millimeters of mercury. That is the partial pressure of oxygen in the system. And CO2 is going to be incredibly small. I think it's only something like 0.25%. So I'm just going to put down that it's going to be, I'm being generous with this. CO2 is probably going to be 2.5 millimeters of mercury, partial pressure of CO2. So that's going to give us about 163 millimeters of mercury. The other, the rest is going to be comprised of non-reactive oxygen, or nitrogen gas and water vapor. Water vapor is actually a gas that contributes to atmospheric pressure. So let's go ahead and look at this here. So let's say that we have the lungs at rest. Let's say that we have the lungs at rest. All right, so these are the lungs, and these are at resting conditions. So we'll say that this is with you just sitting, just a nice exhale, and then sitting there passively, as in you're not actually you're not actively expanding or contracting your lungs. So lungs relaxed. It is going to be equal with atmospheric pressure. However, what's going to happen is if you expand your lungs, when you inhale, when you expand your lungs, you are going to increase the volume and decrease the pressure, which means that gases will be allowed to travel in. But if we look here, we know that actually, I'm going to draw you a different diagram. Sorry if you already started to draw this one. I'm going to draw you a giant alveoli that is inflated with gases. And this is going to I'll sort of explain how each gas travels down its own gradient. Now, in the alveoli, the partial pressure of oxygen is about 100 millimeters of mercury O2. And in the atmosphere, it's 160 millimeters of mercury O2. Now, we also saw that in the atmosphere, the partial pressure of CO2 is incredibly small. And in the alveoli, it's actually going to be more like somewhere around 45 millimeters of mercury CO2. Now, each gas travels down its own partial pressure gradient. Which direction do you think oxygen is going to travel in? Is it going to travel in the alveoli, or is it going to travel into the atmosphere? Well, we know that the oxygen in the atmosphere is more concentrated than the oxygen in the alveoli. So under normal circumstances, oxygen will always flow into the lungs. Carbon dioxide, we see that there's a huge pressure gradient. There's much more carbon dioxide in the alveoli than there is the atmosphere. So carbon dioxide is always going to flow out into the atmosphere. Now, what about the blood? Well, in the blood, there's going to be about, in the venous side of things, about 47 millimeters of mercury CO2. And as far as oxygen goes, there's going to be usually about, I'm blanking on the exact figure. We'll talk more about the exact figure in the next chapter. But there's going to be about, I would say, maybe 60-ish, 60 millimeters of mercury O2. So what's going to happen is that we see that gases are going to travel from, carbon dioxide is going to travel from the blood into the alveoli. And keep in mind the values in the blood are strictly estimates. I'll have a more exact value when we get to chapter 18. But the main idea is that I want you to see how partial pressure gradients work. And then oxygen is going to go from the alveoli to the blood. So we see here, on normal circumstances, let me preface this by saying atmospheric pressure. What we're going to see is that oxygen has a higher partial pressure in the atmosphere as it does in the alveoli. Therefore, following its own partial pressure gradient, because recall that gases, like anything else, also go down a gradient. Oxygen is going to go from the oxygen-rich atmosphere into the alveoli. However, CO2 is much more concentrated in the alveoli than in the atmosphere, so carbon dioxide will rapidly move into the atmosphere. Now, as far as on the blood side of things, well, oxygen's always going to move into the blood because under normal circumstances, there's more oxygen in the alveoli than on the venous side of the blood. So oxygen will diffuse into the blood, and there will be more carbon dioxide in the blood than the alveoli, so carbon dioxide will diffuse in the alveoli. Now, you might be thinking, well, geez, there's basically the same, almost the same um, uh, partial pressure of carbon dioxide in both the alveoli and the blood. Well, keep in mind, this carbon dioxide in the alveoli is constantly being expelled into the atmosphere. So it's more like this 47 is constantly being transferred into the alveoli than into the atmosphere. The gases in the alveoli are basically a snapshot of that moment because it's constantly changing. Now, what's going to happen if you increase in altitude? Well, let's see here. Well, at what we call sea level, we see that the partial pressure of gases in the atmosphere is about 760 millimeters of mercury. What's going to happen if you increase in elevation? Let's say you decide that you want to go climb Mount Everest. Well, at the top of Mount Everest, partial pressure is about 250 millimeters of mercury. About 20% of that's going to be oxygen. I'm no mathematician, but that would make oxygen about 50 millimeters of mercury, give or take. So right here, 50 millimeters of mercury. Now, we have a problem here. Because now what's happened is that the partial pressure of oxygen is going to be less in the atmosphere as it is the alveoli. What that means is that oxygen is going to have a hard time diffusing from the atmosphere into the alveoli because there's now a much smaller partial pressure gradient. In fact, according to this diagram, and it's going to change, of course, because as I said, this oxygen in the alveoli is very short-lived. Regardless, what's going to happen is that there's going to be a very small or no gradient, partial pressure gradient for oxygen. Because of that, oxygen will be unable to properly diffuse into the alveoli. It's also why people that climb at extreme altitude bring supplemental oxygen, because that would raise the partial pressure of oxygen, which would then diffuse into their alveoli. And if you want a much more mild effect of that, if you go to a higher elevation place like Denver, Colorado, you'll see that it will take you a while to adjust to that higher atmospheric pressure. Your body can adapt in order to be more efficient with oxygen usage. But until you adapt, it's going to be a bit rough. That's why many sports teams don't like to play in the Colorado stadiums because the stadiums are built in areas of higher elevations than what they're used to, where the actual players that live there, they've already adapted. Talk some of those adaptations in chapter 18. So an increase in elevation decreases the partial pressure of oxygen, which slows down the rate of diffusion. So once again, increased altitude decreases partial pressure of oxygen, decreases diffusion. Which can lead to, in the short term, a hypoxic state. Now, as far as humidity goes, humidity is a measure of the amount of water vapor in the air. And basically, one thing to note is that water vapor displaces other gases. Displaces other gases. Depending on the area, humidity can either be 0 to 40 millimeters of mercury of pressure. So if there's closer to this 40 side of things, that means there's less gases present and more H2O, which I know that the water is a gas in this case, but this is just to clarify things. However, if there's less humidity, that means there's more gases and less water. What this means that according to this model, in areas where it's extremely humid, there's going to be a little bit less partial pressure of oxygen in the atmosphere, meaning that it's going to slightly decrease that concentration gradient and could make it just a little bit harder for oxygen to diffuse into the lungs. And that's how humidity and altitude affect the partial pressures of gases. All right, everyone. So now we're going to, for gas laws, we are going to relate gas laws to lung function. And we kind of already did, but I thought that I would clarify things a bit. All right, so first of all here, we have the lungs. And I'm going to draw the lungs analogous to, well, I'm just going to keep this diagram pretty simple. So we have the lungs here, and this is the trachea. We know that by now it diverges into two primary bronchi. Then you have the actual lung tissue. Nice, good set of lungs. And the only thing that we have the ability to control is whether these lungs expand or contract. And we actually don't control our lungs, as we talked about. Only thing that you do control is your muscles, your skeletal muscles. Now, we talked about two components here, volume and pressure. Now, when you inhale, what is going to happen is that you are going to increase the volume of your lungs. So when you inhale, what's happening is that you are going to increase the volume of the lungs. Now, if you increase the volume, then according to Boyle's law, then you are going to decrease the volume. Sorry, decrease the pressure. Now, recall that we have something called atmospheric pressure, or ATM. And atmospheric pressure, which is measured in millimeters of mercury, is 760 millimeters of mercury. So what this means is that if our lungs have a larger volume and pressure is decreased, then the gases from the atmosphere are going to diffuse into the lungs. Once again, if the pressure in our lungs decreases, we are going to establish a concentration gradient. So what happens is that when we inhale, we are going to increase the pressure gradient. So let's just say, I'm just going to say for fun, the atmospheric pressure is 760 millimeters of mercury. When you inhale, the pressure in the lungs is going to be, I'll just say 240 millimeters of mercury. That means we have a pretty impressive gradient, right? And gases are going to flow into our lungs. So when you inhale and feel gases going into your lungs, you are not doing anything to draw in the gases. The gases are moving in passively. which is pretty impressive if you think about it. Okay, so atmospheric pressure is not going to change. However, we can change the size of the lungs. And let's say that we're going to go ahead now and exhale. Draw this here. Now, if we exhale, what is going to happen is that we are going to decrease volume. If we decrease volume, we are going to increase pressure. So when you contract your muscles and exhale, what's going to happen is that you are going to increase pressure. So I'm going to go ahead and just for fun, I'm going to list this as 800 millimeters of mercury. So what's going to happen is that you are going to increase the pressure gradient in the other direction. So now you have made your lungs more pressurized than the atmosphere by making the container smaller. And this is how we do the process of respiration. And you're seeing now, that's why it's very important that you have lungs that can expand and contract naturally. Because lungs that are not healthy will have a harder time getting in oxygen or gases in general. Now going back to Dalton's law, I did a pretty good diagram on that. But what that's saying is that if gases can enter the lungs because the pressure is low enough, each gas is going to go down its own pressure gradient. And we generally use oxygen and carbon dioxide for this, mainly oxygen. But we see that at atmospheric pressure, the partial pressure of oxygen is about 160 millimeters of mercury. This is at sea level. I gotta sneak in O2 somewhere here. I'll put an O2. And in the alveoli, on average, it's about 100 millimeters of mercury. So what's going to happen is that now you have a pretty good gradient of oxygen. It's going to easily travel into the alveoli. Now, what happens if you increase altitude? Well, if you increase altitude, then gases become less dense. If you've ever watched a shuttle launch, you'll see that when it takes off, it's surrounded by engines, but then as it goes up, it starts to drop the engines. That's because gases become less dense and there becomes less resistance. That's because the gas molecules, would say they look like this at sea level. And then as you increase in altitude, they're going to look like this. So what's going to happen is that if you increase in altitude, partial pressure of oxygen is going to drop, maybe to 130 millimeters of mercury. So it is going to diffuse, but since there's a smaller gradient, then there's not going to be as fast of oxygen diffusion. Now, if you live in a climate that's significantly elevated, that doesn't mean you're going to be constantly oxygen deprived. What's going to happen is that at a chemical level, your body will become more efficient at finding the oxygen that's already there. We'll talk about that next chapter, but part of the adaptations is that a hormone that your body makes called erythropoietin, that is going to increase the concentration of red blood cells and the protein hemoglobin, and also is that the oxygen is going to be more likely to bind with hemoglobin instead of disassociating. We'll talk about that in next chapter. Hello, everybody. It's good to have you back. And today we're going to be talking about something called spirometry, which is a measure of lung function. Spirometry. So on the x-axis, we're going to have time, and on the y-axis, we are going to have volume. And you can do the volume either in milliliters or liters. I like to do it in liters, but it all comes out of the wash, as they say. Now, for the average human male, the total lung volume, as in if you were to take the lungs and measure all the air that it can hold, it would come out to about 6 liters or 6,000 milliliters. So for the average male, it's going to be about 6 liters. Now for the average female, it's actually going to be a bit different. So for the average female, it's going to be approximately 4.8 liters. And the reason for that is just because lung volume relates to torso size. As in, if you have a larger torso because you're taller, you'll have a larger lung volume. And if you have a smaller torso, you will have a smaller lung volume. This is not something that can be built upon. If you develop a lung volume of 5 liters as an adult, it will stay 5 liters. But of course, that doesn't mean you can't you can't increase your endurance or your athletic performance, because athletic performance, of course, is much more than just lung volume. You can certainly become more efficient. And plus, you'll see that we really don't use our entire lung volume either. So first, we are going to talk about what is called lung volumes. And these are components that we measure during our spirometry lab, which is actually a lot of fun, and I'm really bummed out that we can't do it for obvious reasons. But we're going to start with lung volumes. So I'm going to go ahead and label the x-axis now. And let's have a little fun. Let's do it in some different colors. So 1 liter, 2, 3, 4, and no, this is not the scale. 5 and 6. Now, I'm going to base this on just the average for human male, mainly because I just drew the volumes for it. That and I believe that most sources are based on a volume of 6 liters. All right, so the first thing we're going to talk about, and I'll label this on the side here. Here, let me get this up here so we can have more room. So the first thing that we're going to talk about is lung volumes, as I said. And in red, we are going to do what's called tidal volume. Can't draw with an eraser. Tidal volume. And the measurement for this, or the abbreviation for this, is going to be TV. And it goes from about 3,000 to 3,500 milliliters, and it goes like this. So tidal volume is a measure of a normal inhalation and exhalation. It is a measurement of a normal inhalation and exhalation. What that means, if you were to sit here and just breathe normally, that would be your tidal volume. So what this means is that when you start to breathe, if you're just sitting here breathing normally, unless you're watching this on the treadmill or something, that's what I do. I put on science videos and I just write it out on the treadmill. So if you're like me, you're heading for great or not great places depending on your perspective on it. All right, so your lungs are always, at rest at least, going to be partially inflated. And tidal volume is about 500 milliliters. Depending on your torso size, as I said, it can be more or less. All right, so now we have something called inspiratory reserve volume. Inspiratory reserve volume. And this one's going to be abbreviated IRV, inspiratory reserve volume. And what this one is here, I'm not going to write it down to save space. But at the end of a normal inhalation, how much more can you inhale? So at the top of a normal inhalation, they'll ask you to inhale maximally, as much as you can, and then come back down. So it would be like normal inhale. In fact, you guys can try this too. Inhale normally, then maximally, then breathe out normally. This is your inspiratory reserve volume. How much more you can inhale past a normal inhalation. Okay, now the next one is going to be called expiratory reserve volume, or ERV. This is ERV, and normally I refer to these by their abbreviation. So this is expiratory reserve volume, or ERV. What's going to happen now is that a normal exhalation, so inhale, exhale, at a normal exhalation, how much more can you exhale? So you're going to exhale as much as possible, and then you're going to come back up. This one is kind of uncomfortable to do, but you can try it out. So inhale normally, exhale normally, then exhale maximally. Oh, then inhale normally. Yeah, I don't like this one. All right, so this is going to be called expiratory reserve volume. Now, you probably have noticed pretty fast that you cannot fully deflate your lungs. Now, recall that, and I'll draw this on the side, kind of. Recall that you have the thoracic walls, which are continuous with the parietal pleural membrane, and then you're going to have the pleural fluid. No, this is way too much fluid. And then you were going to have the visceral pleural membrane, which is continuous with the lungs. I know, not the prettiest lungs in the world, but that didn't come out so bad. So you can see here that the lungs are always going to be partially inflated. Recall that Boyle's law is that if you decrease, if you increase the volume, then you are going to decrease the pressure, because the lungs are always going to be attached to the thoracic wall. They're always going to be partially inflated, which allows air to come in from the atmosphere and into the lungs to equalize. So the lungs are always partially inflated because they're attached to the thoracic wall. So I'm going to go ahead and label these now. So this one here is going to be TV, where the arrow is. This one here is going to be IRV, where the arrow is. And then we have ERV, once again, where the arrow is. Now, there's also one more that I haven't talked about yet, and that is residual volume. Residual volume, and this is the amount of the amount of air that remains in the lungs after a maximal exhale. This is called residual volume, or RV. Okay, so these are the lung volumes, but we also have something called lung capacities. We're going to do that here now. Lung capacities. Okay, and lung capacities are 2 or more lung volumes. All right, and the first one is going to be vital capacity. Now vital capacity, and you know what, I need more room, so these ones are going to have to go. You know, on a whiteboard, I almost find it therapeutic to start to erase things, and that also translates over to this board. All right, so capacities. We're going to start with something called vital capacity. And vital capacity is the usable volume of the lungs. It is the usable volume of the lungs. And it is going to be the combination of 3 values: TV plus IRV plus ERV. So it's going to look like this. This here is going to be VC, or vital capacity, not Ventura College. Next, of course, is going to be total lung capacity, since we're talking about maximum volumes. TLC, I think there was a show on that on MTV once upon a time. So TLC is total lung capacity. And it's going to look like this. So this here is going to be total lung capacity. And next we're going to have inspiratory capacity, which is going to be TV plus IRV. So now we have IC, which is inspiratory capacity. Inspiratory capacity, forgot how to spell it for a second. And this is going to be the total amount of air that your lungs can take in. So it would be, after a normal exhale, you would inhale maximally. To avoid our graph getting cluttered, I'm going to continue on to a little bit more. Normal inhale, normal exhale. Normal inhale, end of normal inhale, maximal inhale, then back down to normal. So this space here is going to be inspiratory capacity, or IC. All right. So I encourage you to practice these on your own, because there's no better way to learn than to do it yourself, right? Because on the exam, you're going to see some questions like, this lung volume is a normal inhalation and exhalation. All right, you'll have to choose which one it is. Or, this lung capacity is the maximal amount of air that someone can take in, and is a normal inhale than a maximal inhale. So you will need to know this. And basically, I'm going to give you a graph that looks very similar, but instead of labeling it, for example, I might just say that this is going to be A, this is B, C, so on and so forth. All right, so what this test measures, oh, sorry, there's one more, functional residual capacity, or FRV, functional residual capacity. And this is going to be a measurement of ERV and ERV. So it's going to look like this. It's going to be FRV. Okay, great. So actually, I was remiss in this. I didn't label all of these. So this one is going to be TV plus IRC. TLC is going to be VC plus RV. And vital capacity is going to be these three down here. So I kind of mixed up the colors a bit, which kind of slightly defeats the purpose of using them, but I'll recover. So these are all the different capacities. And what this does is it is going to measure two components of the lungs. One is going to be compliance, which is the lung's ability to expand naturally. And healthy lungs should expand naturally. Okay. Now, on the other hand, we have elastance, and this measures the ability for the lungs to recoil naturally once the force is removed. So compliance is the lungs' ability to expand, and elastance is the lungs' ability to recoil. As we talked about, the lungs are rather elastic. And because of that, they should be able to stretch and recoil normally. If they can't, then there has to be some sort of damage, either through environmental issues, such as, well, in the old days, working in a coal mine, or smoking, living in a highly polluted area, asbestosis, which we talked about in the case study. So there's plenty of things that can interrupt with those processes.